Today we're going to be looking at section 2.3 from our book, Properties of Functions. All right, our objectives today are to determine if a function is even or odd from its graph, from an equation, and then we're going to be determining using a graph, increasing, decreasing, or constant, where a function is going to be kind of having some changes. We will return back to local maximum and minimum, and absolute maximum and minimum when we get to our polynomial units. All right, for this one, we're going to just look at a little bit of information before we get into some picky definitions. Here we have a graph of y equals x squared that I'm going to plot. So 0, 0, 1, 1. When I plug in 2, I get 4 out for the parabola, the y equals x squared. So that's just a parent function that we're used to, hopefully very comfortable with. So I'm going to sketch my parabola. Okay, my square function. And so what is this asking for us in this second part? It's asking us to graph y equals opposite of x quantity squared. So that means, let's say I wanted to plug in the point 2. Okay, what would I get out for this second graph? So if it's y equals parentheses opposite, and I'm plugging in the number 2 and quantity squaring it, that's going to be opposite of 2 quantity squared, but it's still going to equal 4. Okay, if I want to plug in the number opposite of 2 into this second equation, it's going to be y equals opposite, and I'm plugging in opposite of 2, or negative 2, quantity squared. So really that's going to become, watching your parentheses, it's a minus, so it's actually going to be positive 2 quantity squared, which is 4. So what this is saying is when I plug in 2 or opposite of 2, I get the same output, and that's going to be key. This graph then, also how are the graphs related? Let me kind of get rid of some of that. They are related that y equals f of x and y equals f of opposite of x are going to be the same graph, and they're reflected. The points lie on the same graph, and they reflect over the y-axis. So symmetry, where do graphs fold over, are going to be key for today. Okay. Definitions for today: a function is even if for every x in its domain, the number opposite of x, you might use negative x, but opposite of x is also in the domain, and, very picky notation here, f of opposite of x equals f of x. And when we get to algebraic testing, that's how we're going to justify it. So pre-calc is not always just about looking at the graph or just saying yes or no if it's even or odd. It's asking you to justify it, kind of like a 2-column proof in geometry. So if we want a function to be even, it's a very elite category. Actually, many functions are not even, but it has to have this property algebraically: f of opposite of x equals f of x. For an even function, for every point x comma y on the graph, the point opposite of x, y, is also on the graph. And that was what that previous example was showing. And the theorem then is a function is even if and only if, so if and only if is IFF if you want to learn some fun math abbreviations, the graph is symmetric with respect to the y-axis. So if you think of your most basic parent function with an even degree, y equals x squared, that is going to be a function that has symmetry over the y-axis, but not just polynomials can have symmetry over the y-axis. Y equals absolute value of x, not shifted, is also going to be an even function. However, if you took a function like the absolute value of x and you shift it, okay, this shift right here, we're going to recap transformations as a shift right to, then right now this function, if you shift it right to, is no longer even. Okay, so transformations and movements are going to be very picky. More functions are neither even, or soon to be what we'll talk about, odd. So you have to be kind of careful about saying, oh, if it has an even degree, it's got to be an even function. And we'll discuss that as we move forward. Okay, what is an odd function then? So even functions have symmetry to the y-axis. Odd functions are if we're in the domain every x, then opposite of x lies in there, but there's one other piece of information. Then f of opposite of x has to equal the opposite of f of x. And that is a lot of new notation. Okay, bear with me, we'll kind of work through it. So here's a couple of pictures. This is the picture, it's a little bit small with the equation y equals x to the third, a very basic odd degree. Okay, that doesn't guarantee that it's going to be an odd function, but it has points on the graph. So this point up here, if I plug in 2 and I cube it, I get 8. And if I plug in opposite of 2, I get opposite of 8. You can get negative out when you cube them because it's odd degrees. So that's going to be really, really important. This is going to be an odd function. Here, the linear function y equals x also has respect to the origin on that. And then this last one, though, is not going to be odd. It's still a cubic function. I know you can't read the equation. That's perfectly fine. That wasn't really what I was going for. It could rotate around and fall on top of itself, but it's not going to be at the origin. So this part right here can rotate and fall onto itself, but it is not around the origin. So for every odd function, for every point x comma y on the graph, the point opposite of x, opposite of y have to lie on the graph. So that's what's happening up here in our cubic function, x to the third. And so more graphically, a function is odd if it has symmetry around the origin. So the O's go nicely together, O and O for odd and origin. So many functions are going to be neither even or odd, but if they are, they have this special property about their ordered pairs. All right, so here's an example of some graphical representation. Determine whether the graph, so these are the nice ones for us graphical learners, there's a little less work involved, just understanding the properties, if it is an even function, an odd function, or neither even or odd. So we're just looking for symmetry. So part A has symmetry beautifully over the y-axis. So that function, I even have it animated, is going to be even, symmetric to the y-axis. The next one is neither even or odd, because this point up here is not around the origin. Even though this right side of the graph could then rotate around to the other side, it is not at the point of origin with that. So that will not work with that graphically. But part C, right here at the origin, yep, that will be going to be even or odd. Here we have a little bit of animations. That will rotate around and fall onto that. So again, the point x, y lies on the graph, but also the point opposite of x, opposite of y must lie on the graph in order for it to be an odd function. All right, so here are some algebraic ways to determine if a function is even, odd, or neither. This will be much more taxing on our brain, a little bit more challenging this year, because you're proving it. You're like an algebraic proof. So it's not so much as just getting the answer of, oh, that's even or that's odd. It's actually more in depth of showing or justifying it, like a two-column proof in geometry, prove two triangles to be congruent. Now we're trying to prove that if a function is even, odd, or neither using algebraic step points. So for part A, what I'm going to do is I'm going to go ahead and test, again, one of the properties is if a function is even, then f of opposite of x should equal f of x. Okay, and if it's odd, a little bit more in depth, f of opposite of x has to equal opposite of f of x. All right, so there's a little bit different notation with that. So it's actually best to check if something's even first, and then you can go ahead, and if it's not even, then there's a chance it could be odd, but you're not going to be, there's only one special case where you have an even and odd function with that. Okay, so here for this one, I'm going to test if it is going to be an even function. So I'm going to test if opposite of f of x, does that kick out the original function f of x? Do we get the same function back out? So I'm going to substitute in with parentheses opposite of x raised to the third plus 5, and then it has to have parentheses, otherwise it's going to be minus x opposite of x. And then you're going to clean up the equivalence to it. So this is going to be when we have opposite of x raised to an odd power, that is going to stay negative. Okay, an odd raised, a negative opposite value raised to an odd power is going to be opposite of x to the third, and then 5 times an opposite of 5 is minus 5x. Okay, so then when you're done cleaning that up, you want to look back at your original equation. This does not equal f of x. Therefore, it is not even. Okay, so then the next step is it's odd. And now if you are trying to pick up on a little bit of maybe some cues, these degrees are both odd here, x to the third and plus 5x to the first. That doesn't guarantee that it's going to be an odd function, but it's something to consider and look at with that as well. So what's going to happen here is we're going to test, this is right here, f of opposite of x. So what we're going to see is f of opposite of x equal to opposite f of x. So how do we do that? I'm going to go ahead and take this f of opposite of x, and I'm going to go ahead and clean it up a little bit. All right, so I'm going to go ahead and it's opposite of x to the third minus 5x. So I'm going to go ahead and substitute or pull out an opposite symbol or a negative symbol out of all of it, and we're going to get x to the third plus 5x. So that opposite of x right there, now if we take a look at it, this is f of x, and we have a negative out in front of it. So since f of opposite of x equals opposite of f of x, then this function is, yes, this is going to be an odd function. All right, so that's how we can determine odd functions. All right, I'm going to go ahead to the next slide where we have a little more room for B and C to talk about them. Okay, so here we have the same problem for 5. Let me just pop that up. So we checked f of opposite of x equals, and we used substitution and plugged in the opposite of x into both places and replaced it. It's like if we were evaluating the function at f of 2, we would plug 2 into the places where there's x. But now we're not evaluating it at a particular number. We are testing an opposite of x value. Okay, so then we take out a opposite of x, or I factored out a leading coefficient, or the negative symbol, excuse me, and we did end up with that one. So that one is going to be odd, and it must have symmetry and rotate around with respect to the origin. All right, part B is going to be a power of 2. So right away you're kind of going to be like, that's a parabola. Can we get that to have symmetry? Remember, even is going to be the y-axis, if you're a visual kind of learner, and odd is going to be the origin. Okay, so how do we test this one? I'm going to test it for even. I'm going to test g of opposite of x, and I think I have this animated, so let me back up. There we go. And I'm going to substitute it in opposite of x, and if you notice right here, when I square a quantity, and if it's negative, it's going to become positive. So right away I can clean it up. The negative 3 stays the same. This right here is function g of x. Therefore, this function has function is symmetric with respect to the y-axis. I'm not graphing these. So in pre-calc, we want to be able to elicit different tools, and one of those tools is not to always have to graph something. Letter H, we're going to test here. So we're going to test and plug in h of opposite of x. Okay, so we have negative 4 as our leading coefficient. I've substituted in with parentheses opposite of x to the third. And then an opposite of x raised to an odd power is going to stay negative. However, 4 is negative as well. So a negative and the negative become positive, and I ended up with positive 4x to the third plus 1. That is not equivalent to the original function h. So again, in order to be even, you have to have, in this case with that notation, h of opposite of x has to equal h of x. And that does not happen here, all right? This does not, when I plugged in opposite of x, I did not get the original function back out, meaning there's no symmetry to around the origin. And so we will not be either odd or neither. It's just going to be a function. It's not an elite one in the category. Okay, last little bit, even if we're increasing, decreasing, or constant from a graph. So here, increasing is going to be when is the function going up, decreasing when is the function going down, and we're going to read it from left to right like we would read a book, and then when is the function constant. All right, so let's see how we can look at that. So I'm going to move to the next slide, and we're going to test that out. All right, so increasing, decreasing, constant. Okay, so for this one, the function is going to be increasing whenever it's going up, and we don't say it's increasing between two ordered pairs. We actually say it's increasing. We're only looking for the x values. For what x values is the function increasing? So it's going to be increasing between -4 and 0 for the x values. Typically, we say an interval notation right here. Okay. However, our book does do this a little bit off in many of our, like our opinion of math, especially from calculus. At the endpoint right here, the function is neither increasing or decreasing. But for whatever reason, our book decides to use brackets. So when you type in the homework, you're going to have, in the digital book, you're going to have to use brackets for the areas of increasing and decreasing on that. All right, where is this function decreasing? This function is decreasing when it is going down. So it's going down in two different locations when you read it from left to right. So we would say, what are those x values between? So -6 and 4, and 3 and 6. So there's set notation, but it's going to be bracket notation, -6 to 4, and 3 to 6. And again, our book is going to use brackets. I don't really agree with it, but we're going to kind of go with that because it's already typed into the program. And they're going to have you separate them with a comma in order to type them into your answers tonight. So that's really important that it's going to have a comma between it with the different brackets. But it really should be parentheses because at the end points, it's neither increasing or decreasing. But that's what we're going to go with for now. All right, where is the function? Constant. Okay, the function's constant where it's not going increasing or decreasing. That's right along here. Again, what are those x values? Not between the ordered pairs. And it's going to be constant between 0 and 3. So that is going to be our lesson for the day. I'm just going to pop up kind of the answers. Again, our book is going to use brackets. The other notations aren't incorrect, but it's going to use brackets, and you're going to separate them with commas when you type them into the digital book. All right, thank you.